You've learned Python's syntax, its object model, even how to ship a REST API. This video is about the next jump, the patterns and disciplines that separate a script that works from a system you can actually run in production. We'll cover 5 Level 4 lessons back to back: reusable design patterns, metaprogramming for framework-level tricks, building a real authenticated API, testing it properly, and closing the loop with security. Each one builds on the last, so stick with the whole arc. First stop, design patterns, but the Pythonic versions, not the Java textbook versions. Python's first-class functions and dynamic typing mean a lot of classic patterns get dramatically simpler here. We'll look at 4 of them: factory, strategy, observer, and singleton. A factory centralizes the decision of which class to instantiate. Here, a notifier_factory function takes a string like email and looks it up in a dictionary of notifier classes, so adding a new notification type is just one new dict entry instead of a growing if-elif chain scattered across your code. Strategy lets you swap an algorithm at runtime, and in Python it barely needs a pattern at all, you just pass a function. Here, total_price takes a discount_strategy parameter, and 3 completely independent functions: no discount, 10% off, bulk discount can all be dropped in without touching total_price itself. Observer decouples something happening from who reacts to it. This is the same idea behind webhooks and pub subsystems. This event bus lets any number of listeners subscribe to an event name, so when publish fires an order_placed event, both the email confirmation and the inventory update run independently, and neither knows the other exists. Singleton guarantees exactly one instance exists. In Python, the simplest singleton is often just a module. It's cached in sys.modules and only ever imported once. But when you need a class-based singleton with real initialization logic, overriding new lets you return the same cached instance every time, which is exactly what this logger class does here. For patterns, one theme: Python's dynamic features, first-class functions, module caching, dunder methods let you get the benefit of these patterns with far less ceremony than a strictly typed language needs. Next, we go one level deeper, shaping how classes themselves get built. Metaprogramming is code that manipulates code classes that customize how other classes get created, and tools that let you inspect or even generate code at runtime. It sounds exotic, but frameworks like Django's ORM and SQL Alchemy lean on exactly these tricks. Every class is secretly an instance of a metaclass by default type. Defining a custom meta class that subclasses type lets you hook into class creation itself. Watch the print statements here: creating class myClass and initializing class myClass both fire at import time, before a single instance of myClass exists. Full metaclasses are powerful but heavy. For the common case, do something whenever a subclass is defined. A init subclass is a plain class method hook that does the same job with far less ceremony. Here, every CSV exporter and JSON exporter that subclasses plugin registers itself automatically, no metaclass required. You can also build classes and functions dynamically, from strings, at runtime. Calling type with a name, a tuple of base classes, and a namespace dictionary constructs a full class on the fly. This is literally how libraries like data classes generate fast init methods under the hood. Exec can even compile a function from a raw string, though that's a tool for framework authors, not everyday business logic. The inspect module lets you interrogate objects instead of guessing. Inspect.signature reads a method's parameter type straight off its annotations, and inspect.getSource pulls back its actual source code. Both are how tools like IDEs, debuggers, and documentation generators work under the hood. Metaprogramming is rarely something you reach for in application code day to day, but recognizing it in your ORM, your test framework, your web framework explains a lot of otherwise magic behavior. Now let's put these language-level tools to use building something real, a production API. This is where design meets deployment. We'll take a FastAPI service through 5 things every production API needs: real authentication, cross-cutting middleware, safe cross-origin rules, versioning, and abuse protection. Authentication here uses the OAuth2 password flow with JSON web tokens. Passwords are hashed with bcrypt through passlib and never stored in plain text. Verify_password checks a login attempt against that hash, and create_access_token issues a signed, time-limited token that get_current_user later decodes to identify who's calling. Middleware runs on every single request without you repeating code in every route. This example tags each request with a unique ID, times how long the handler took, and stamps both onto the response headers exactly the kind of logging and observability you want everywhere, not copy-pasted into 10 endpoints. CORS middleware controls which frontends are allowed to call your API from the browser. The critical rule here: never combine a wildcard allow origins with allow credentials true. That combination quietly disables the browser's same origin protections for authenticated requests, which is a real, common misconfiguration. Prefix-based versioning is the simplest way to evolve an API without breaking existing clients. Two routers, one mounted at /API/v1 and one at v2, can return different response shapes for the same logical endpoint, and you retire the old version on its own schedule. And rate limiting protects the server from being overwhelmed, accidentally or otherwise. SLAWAPI keys a limit by client IP, so a client that exceeds 5 requests a minute on this search endpoint gets a 429 too many requests response instead of eating up server resources. That's a real, defensible production API, authenticated, observable, versioned, and protected. But none of that matters if you can't prove it keeps working as you change it. That's testing. Unit tests you already know. This lesson is about testing a real system, managing expensive setup, faking external dependencies, and finding edge cases you'd never think to write by hand. PyTest fixtures default to running fresh for every single test, which is safe but can be slow. Setting scope to module or session shares expensive setup like a database connection across every test in a file or even the whole run, as long as you're careful nothing mutates that shared state. Mocking swaps a real dependency for a controllable fake, so tests stay fast and deterministic. Here, a mock stands in for an email client. The test never sends a real email, but assert_called_once_with still proves send_welcome_email called it correctly, with exactly the right arguments. The single most common mocking mistake is patching a name in the wrong place. You patch the dependency where it's looked up whether_service.requests.get not where requests was originally defined, or the mock silently won't take effect and your test will quietly be testing nothing. Property-based testing flips the script. Instead of picking individual examples, you describe a property that should always hold, and hypothesis generates hundreds of inputs including nasty edge cases trying to break it. When it finds a failure, it automatically shrinks the input down to the smallest case that still fails, which makes debugging dramatically faster. With fixtures, mocks, and property-based tests in your toolkit, you can trust your test suite to actually catch regressions, not just prove the happy path works. Last stop, making sure the system you just built and tested is actually safe to expose to the internet. Every vulnerability class here shows up constantly in real breaches, and every fix is genuinely simple once you know to look for it. We'll cover 5 secrets: SQL injection, command injection, unsafe deserialization, and password storage. Never hardcode an API key or credential into source code. It lives in your Git history forever, even after you delete it. Reading from an environment variable, and failing loudly with a clear error if it's missing, is the minimum bar. Production systems should go further with a dedicated secrets manager that supports rotation and auditing. Building a SQL query with an F string is one of the oldest and still most common vulnerabilities in software. If username comes from user input and gets concatenated directly into the query string, an attacker can pass something like or1=1 and read your entire table. Parameterized queries let the database driver handle escaping safely instead. The same trap applies to shell commands.
Passing shell equals true with a string built from untrusted input means a filename like report.txt:/rm-rf/ can run an entirely different, destructive command. Passing arguments as a list instead means that semicolon is just a literal character, never shell syntax. Python's pickle module can execute arbitrary code the moment you deserialize untrusted data. Never call pickle.loads on anything that came from a user or the network. JSON can only ever represent plain data, never executable code, which is exactly why it's the safe default for untrusted input. And passwords always go through a slow, salted hashing algorithm like BCRYPT, never plain text and never a fast general-purpose hash like SHA-256. BCRYPT's deliberate slowness is the whole point. It makes brute forcing a stolen password database expensive enough to not be worth attempting. 5 lessons, 1 through line. Python gives you clean, expressive tools for design, introspection, real APIs, rigorous tests, and safe defaults, but every one of them still requires you to make the deliberate choice to use them correctly. That's the master-level arc: patterns that scale your design, metaprogramming that powers your frameworks, a production API with real auth, tests that actually catch regressions, and security habits that keep it all safe. All 5 lessons are linked below if you want to work through the code yourself.